Okay, good afternoon. Let us start our lecture. Before that, do you know when will the midterm test begin? Huh? October. The date? You received the announcement? Okay, good. So it is 5th of October, if I remember correctly. It's a Saturday. It's a Saturday morning. All right. So just let you know. It's just after you enjoy your or work hard on your 1 week break, then the following Saturday will be the midterm test for 2, 3, 3, 4. All right. Okay. So in the last lecture, we talked about probability function for discrete random variable. So first of all, we talk about random variable. We also talk about discrete random variable, which means that the possible values of x are countably infinite or finite. All right. So here is an example of a probability function, which consists of the random variable, which means that you have the value or the range of the values, and associated to each value there is a quantity represented by this f of x. All right. So that will reflect how likely the random variable takes that value. So that's a probability function. So basically, you can consider a probability function is a collection of two order pairs. A collection of order pairs. One is the x value. The other one is the probability of the random variable takes that value. So in this example, so for 1, then it will be Cx. So this is one part of the probability function. Then 2, okay, sorry, this is x, C, sorry, it's C. X equal to 1. Then this one is 2C. Then 3C. Then 4C. Right? Because the substitute x equal to 4. 5C. Do we have that? Do we have that? No, because the f of x equal to cx only when x equals to 1, 2, 3, or 4. Beyond that, it falls to the other one called otherwise. It's equal to 0 otherwise. All right? So you don't have such pair in your probability functions. Okay? So, as a probability function, that means this particular f must be positive. Okay. Must be greater or equal to 0. And also sum up for all possible value of x, sum up all this f of x should equal to 1. All right? Now, so today we continue by looking at another interpretation of a probability functions. So let's think of it. A probability functions, all right, basically can be used to model or to tell us something about the population, a finite population. All right. So consider select at random a student who is among the 35,000 registered for the current semester in NUS. All right. So it's a finite population. It's a student population. Consists of 35,000 of them. All right. Then we select one of them. So you can let x be the number of modules for which the select students register. And suppose that x has a probability function. All right. Okay. First of all, x is the number of modules a particular student that we select. All right, how many modules it takes. that is represented by x. So x is a random variable. Okay. First of all, x is a variable. Why? You can take 5 modules. You can take 4 modules. You can take 3 modules. Can you take 2 modules in a semester? Cannot, huh? It concerns you, not me. I don't have to take modules. Right? Can you take 2 modules? Yes, 1 module? 0 modules? I think you need approval for 0 modules. Any discount for taking 2 modules? No, right? I think you have to pay full fees. Right? But I don't know. Okay, I really don't know. For average, it's 5 modules. But you see, students, you don't know whether he takes 2, 3, 4, 5. So that is a variable. All right? Now, so if I select students, so ask the students, how many modules do you take this semester? So he already registered for, let's say, 5 modules. So the answer is 5. He registered for 5 modules. Then where does this randomness come in? Now, just like toss a coin, if I toss a coin, I ask you what is the outcome? It can be head, can be a tail, right? I have not tossed it, but you know that possible outcomes are head and tails. So the same thing. If I select the students and ask him how many modules he takes, then of course there's a fixed number. But now the randomness comes in because I can select randomly a student. All right, you don't know who is being selected, so that is the randomness part. All right, so X represents the number of modules taken by students, but because this student is randomly selected, it can be anyone. So that's why it's random. So if it's random, naturally we'll ask, okay, so what's the chance that the student that I select take 0 modules, 1 modules, or 2 modules? All right? So that's how we interpret the probability in a finite population. Basically, is look at it. If in the 35,000 student population, none of them registered 0 modules in that semester. So that means the probability of x equals 0 is 0. Let's say out of 35,000, all right, there may be 1,000 taking 1 module. So in other words, the chance that I pick that student which belongs to this group with 1 taking 1 module is 1,000 over 35,000, or 1 over 35. All right? So that probability may be translated as the proportion of individuals in the population that has that values for the random variable. Okay? So in this case, suppose I have, even I have 7. So 2% of the students take 7 modules. All right, out of this 35,000. So that's how we interpret the probability functions. All right. It's the proportion in the population that has that value. So you can think of it, it's something like this. We look at students, 35,000 students. But I can replace each student by the modules, number of modules that he takes. So I have 35,000 numbers, range from what we have here is from 0 to 7. But they are not all the same proportion. Obviously, most of the students take 5 modules. About 40% of students take 5 modules. All right? So only 1% take one modules. So that's our probability function of this random variable x, which is the number of modules. All right, randomly select students. All right, tick. All right, so that's how we interpret it. Okay, so you see here, forget about the students, look at the modules. All right, so there are, in this 35,000, there's 1% of them are 1s. All right, 2% of them are 7s. For 39% of them are 5, and things like that. All right, so it consists of the values. It's 1, 2, 3, 4, 5, 6, 7, and the f of x is the proportion in this population that have those values. So we consider this as a model to describe the population. All right, so now we move on to talk about continuous probability distributions. So, of course, it's continuous, so it must be different from the discrete. So what is it? So, suppose the range space, all right, is either interval or collection of intervals. All right. So what it means is that you recall what is a random variable? Random variable is supposed to be a sample space, all right, and then we have this real line, or I call it Rx. So through this way, I link up the sample points to the values. So if the space here, the range, that means all the possible images are basically falls in an interval. This interval can be just like that, or can be from minus infinity up to infinity, or maybe like that, taking this, just this part and this part. So long as your range of x is not finite and is not countably infinite, then it's considered as a continuous random variable. All right? It can be a very short interval. It can be a long interval from minus infinity up to infinity. Or it can be just a few intervals, non-overlapping intervals. All right? So then we say that x is a continuous random variable. All right? So here is the definition. F of x is the probability density function. All right? I will explain why it's called density. All right? But you can see that for any x, for the random variable x, we associate with a value which determined by f of x. F of x is a function. And this f of x, that means this number has to be bigger or equal to 0 for any x in the random variable. All right? Then, instead of doing summation, we do integration. Integrate the probability density functions over the range is equal to 1. Or is integrate from minus infinity to infinity. Okay, so what's the difference between these two? So you can think of it like this. So it's between, maybe easiest, between A and B. All right? So x takes value here. And the number or f of x associated with any values between A and B will be just a constant. In fact, 1 over B minus A. All right. So that means for any number here, I will consider the f of x is 1 over B minus A. So that it will be like this. Outside the interval A and B, the f of x is defined like that. All right? So in other words, this represents how x, this random variable x behaves. So it says that if x, this random variable, takes the values outside less than A or bigger than B, then the f of x, this number associated uncertainty, is 0. But while within A and B, it takes the value 1 over B minus A. Does 1 over B minus A depends on x? What I'm saying is that f of x equal to 1 over B minus A. when x is between a and b, and 0 otherwise. All right, that's how I define the function. So now I'm asking, okay, does f of x depends on x? It depends on the x through the interval, so long as x is between a and b. Then you take this form. If not, if outside a, interval a and b, then you take another form. Then another form is 0. So now my question is that, okay, now I know x is between a and b. So does f of x depends on x? Why not? I don't see any x in the expression 1 over b minus a, right? So that is called uniform distribution. Basically, that it does not depend on x, so long as you know that x is within this interval. It does not rely on exactly what x is, so long as it's between a and b. All right? Okay. So here it says that if you consider integrate f of x dx, basically you are getting this area. Remember, integration is just something like getting the area. So this area is sum up to 1. Sum up to 1. All right. So, in other words, the chance that x falls between a and b is equal to 1. That is what it means, right? X must be some value between a and b. So if I ask, what is the chance that x between a and b? And the answer is 1. What's the chance? The chance is definitely is between a and b. It cannot be outside a and b. So this way of writing things, all right, is basically is saying that the chance that x falls between a and b. Later I will explain why this represents something like that. All right. Okay. Are these two the same? So here I try to explain. I don't know whether you understand this one. So it's just saying that, okay, I do the integration. For those who forget about your integration, you have to revise it. All right. Now this one, when I integrate this one, the f of x take different form. So you have to consider the range for which the f of x equal to a particular form. In fact, there are 3 range. The first one is from minus infinity up to a. What is f of x? When x from minus infinity to a. What is f of x? 0, right? Then from a to b, then what is f of x? 1 over b minus a, right? And then from b onwards, f of x will take another form. So it is 0. All right? So in other words, is integrate from minus infinity, for this example, up to a, f of x is 0. Then from a to b, f of x is 1 over b minus a. Then from b to infinity, it is 0. So you can see that integrate 0. This one is 0, this one is 0, so it's equivalent to this part. All right? So I want you to be aware of the 2 things. First of all, in general statement, the condition, the second condition, just like the discrete, sum all the f of x should equal to 1. Here you integrate from minus infinity to infinity, the density f of x should equal to 1. All right? So equal to 1. So that, but if there's some range, some interval, will have a PDF equals 0, then you can ignore those parts or drop those parts. All right? So this is equivalent to what we see point 1 and point 2 for the discrete case. This is equivalent to the discrete case, sum of f of x equal to 1. Here, instead of sum, we do the integration. All right? Then for any C and D, where C and D is within the range of X, is a subset, this interval is a subset of the interval for which your random variable takes value. Then the chance of X between C and D is integrate from C to D f of X. All right? Now, basically like this. You can consider this is a function f of X. All right? So it represents the density. It means that if it's here, then you have a bigger f of X. It means that it's more dense. All right? Or the probability seems to be higher. All right? But what we really talk about is that, let's say this is C, and this is C plus delta C. Mathematicians, you like to use Greek letter, delta C. So it's saying that the random variable between C and C plus delta C, this probability, which is, that means how likely I form, the random variable takes the value here. So I'm telling you, this is equal to f of X, the density function, times the width. Or you can consider this as this. Probability, this is the probability, right? That C falls within this range. If I divide by delta C, what does it mean? It means it is the density. Right? How dense it is. If it's very dense, then the probability that X falls between C and C plus delta C will be bigger. In fact, the probability, strictly speaking, the probability is only this part. It's not a rectangle. This one, when you multiply f of X, or f of C, all right, times this width, it gives you a rectangle. It's not exactly the same. So, now here's the magic part. I put delta C very, very, very small. Right? So, here, you still can see that it's not a rectangle, right? It's still missing this part. But when delta C getting closer and closer to C, then it's like this. So this difference is very small. If you find that it's not small enough, then get closer to C. So that's, we call it limit. So that's represent the density. All right? So PDF for continuous random variable is a number to reflect not the probability, but how dense the probability is at the point X, So you must appreciate this one. Otherwise, you cannot tell, because sometimes the PDF can be bigger than 1. How can a probability bigger than 1? Of course you cannot. But you can have a density bigger than 1. All right? It's very dense over this particular range. All right? So want to find X between C and D, I just to integrate the density. So the same picture. All right? If this is C and this is D, so the probability that falls here, according to this density function, it will be this area. So I integrate from C to D, f of X. All right? Okay. So, you notice what's the difference between, okay, this one, all right? So represent the area under the graph when X equals C to up to X equals D. So it's like that. All right? Now, for X equal to a particular value, all right? So in other words, X less or equal to X0 less or equal to, what is this probability? Right? Are they the same? Are they the same? Of course they're the same. You're saying that x bigger than this number. At the same, bigger or equal to this number. At the same time, it's also less or equal to this number. It can only happen when x equal to x naught. Correct or not? All right, so it's equivalent to integrate from x naught to x naught. The same f of x dx. And the answer is 0. Mathematically, it's 0, right? But what does it mean? For continuous random variable, the chance that the random variable takes a particular value is 0. That's how we interpret it. For example, your height. All right? To me, it's a random variable. It depends on which home I select. But let's say measure of your height. So how tall are you? Or maybe for myself, okay, I say 1.76, but I'm not really 1.76 meter tall. All right? Maybe 1.761 is still not accurate. 1.7612, still not accurate. So let's have 100 decimal place, maybe still not the correct height. So my point is, for continuous, it's very hard to hit that particular value. So that's why the probability of x equal to a particular value for a continuous random variable, all right, is equal to 0. All right. So remember that's important. But it only applies to continuous random variable. But discrete random variable, x equal to a particular value with certain probability. Huh? And this x naught can be any numbers. All right, the probability x equal to a fixed value is 0. Because of that, so all these are true. You don't care about whether it's the inequality is strictly inequality or just equal inequality. All right, less or equal or greater or equal. All right. So all these are considered the same. This only valid for continuous random variable. I have to stress for continuous random variables. Discrete random variable, then all this may be different. This is also very, sometimes very confusing. Now I'm saying that probability of A equal to 0, all right, does not necessarily imply A equal to empty set. This is true, but the reverse is not true. Probability of empty set is equal to 0. Or let me put it this way. If A equal to empty set, then probability of A is equal to 0. All right? This is true. But the converse is not true. This is very, sometimes people do not aware of that. Okay? So, let's say I toss a die, right? I toss a die. What is the chance that I got a 7? 0, right? But it does not mean that 7 is not, it does not mean that 7 is not in the, I can ask you, okay, what is the probability of a set with 1, 2, 3, 4, 5, 6, 7, including 7, all right? So, okay, my point is like this. Toss a die. I consider this event, this set, 7. Is it empty? A set with a number 7. Is it empty? Hey, you are not blind, right? This is 7, Not nothing. So it's not an empty set. But the probability of having a 7 for tossing a die is 0. All right? So that's what I mean. All right? You have a set. It has something in it, but the probability of this something happens or occurs is equal to 0. Okay? So you have to differentiate that. So if I say that this set is empty, then the probability of this set is equal to 0. But the set is not necessarily empty if the probability is 0. So in other words, you can have a set, have something in it, but the probability of it is 0. So you must able to distinguish between the probability and whether the set is an empty set or not. All right? Then, if x assumes values only in the interval a, b, then we may simply write f of x equals 0 for all x outside this interval. Getting a habit, because we are dealing with the real line. So getting a habit to know how f of x behaves, although f of x equal to 0. It's the same principle. So this is the real line. This is AB, all right? And my PDF is defined over this range. Outside that, they are 0, all right? Now, it does not mean that this set is not there. It's simply saying that the chance that x takes the value here is 0, all right? This is still there. Physically it's still there. So when you write f of x, so it's better to describe from minus infinity to infinity. But usually it's understood that if I only mention f of x equal this form when over a and b, then it means that outside that is 0. But it's better to define or write it down explicitly that outside that range, outside that AB, the density function is 0. Okay, let's look at some example. So with a random variable which is continuous and defined equal to Cx when x is between 0 and 1. Outside this range, the f of x equal to 0. So what we're supposed to do, make sure that this is a well-defined PDF. So you need to check two things. The first one is that whether it's always bigger or equal to 0. So since x is between 0 and 1, so long as if c turn out to be positive, then f of x is bigger or equal to 0. All right? I don't know, because I have figured out what is c to meet the two criteria, such that f of x is, the first criteria is that f of x is bigger or equal to 0. The second one is integrate from minus infinity to infinity f of x dx equal to 1. That means sum up the area under this curve, PDF curve, equal to 1. All right? So, after I find C, all right, make sure that it's well-defined, then I start to find all these probabilities. Okay, so how to do it? So first of all, we figure out, okay, it's supposed to be from minus infinity to infinity f of x dx. All right? I want it, this is my equation. I want to solve this equation. In this equation, it involves the c. This one is equivalent to integrate from minus infinity to 0, 0 dx, plus integrate from 0 to 1, cx dx, plus integrate from 1 to infinity, 0 to dx. All right? So I want this one to be 1. It seems stupid to write so many terms, but getting a habit to do it. So that this one, integrand is 0, so this is 0. Integrand here is 0, so it's 0. So we're left with this one. So in other words, the equation is 1 equal to this one, with c as an unknown. We try to solve for c. But before that, we have to complete the integration. So after you do the integration, it's c over 2. So we need to put c over 2 equal to 1, therefore c equal to 2. C equal to 2. All right? So f of x now equal to 2x, where x is between 0 and 1, and equal to 0 otherwise. All right? Now, after that, now we can answer the questions. What is the probability of x less or equal to half? maybe you can use some software to see how the function look like. I think the function looks like this. This is the x from 0 to 1, 2x. So it's something like that, right? So now we are asked the probability of x less or equal to half. This is half. So we want to know the probability that less than it. So we just get this area. Or in other words, we integrate, this one's supposed to be integrate from minus infinity to half, f of x dx. All right? From minus infinity up to this point. But from minus infinity to 0, the PDF is 0. Then from 0 to half, and 2x dx. All right? I believe that you know how to do the integration. Right? It's quite straightforward. So you do the integration, substitute the limits, and you got 1/4. So in other words, the chance that this random variable has a value less than half, less or equal to half, is equal to 1/4. Only 1/4. Is it reasonable? Huh? Is it reasonable? I mean, why is it not half? Because the density tells us that when the x is small, all right, the density is equal to 2 times x. But that means as x getting bigger and bigger, the density getting double, all right, 2 times it. So that's why the later part has a higher density. So the x falls in the range close to 1 has a higher probability. Okay, then between 1/3 and 2/3, so this time is much easier because now you already specify the lower limit and the upper limit. So if I draw the graph, so it's like that. So this is the part, and we're looking at 1/3 and 2/3. So in other words, we're looking at this area. This is the probability of x falls here between 1/3 and 2/3. So the answer is 1/3. Oh, 1/3 is it by coincidence? You see, I divide the range, 0 to 1/3, 1/3 to 2/3, 2/3 to 1, 3 equal parts. It turns out that the middle portion, the chance that x falls between 1/3 and 2/3, turn out equal to 1/3 of the probability. You understand what I'm trying to? Is it a coincidence? All right. The range is divided into 3 equal parts, and then the probability fall in the middle portion is also 1/3. But if you check this one, is it 1/3? No, right? You can work it out. It's not 1/3. So it's just by coincidence. This difference is 1/3. Turn out the probability is also 1/3. This is just a coincidence. All right? Yes, no matter what you get, if you find it is very interesting, all right, ask yourself whether this is by coincidence, just happens to like that, or is really can be proved, can be shown is true in general. So here I'm saying that I take the middle 1/3 portion, and the probability turn out also 1/3. So I ask whether this is a coincidence or this is the real stuff. Whenever you take the middle 1/3, the probability is 1/3. So that's my question, but this is just by coincidence. Then finally, x bigger than 3/4. So this means that you are considering integrate from 3/4 to infinity f of x dx. So I keep writing this because I want you to remember it's f of x. This is the range. Whenever any x bigger than 3/4, so can be x can be 2, can be 3, can be 10. Right? It satisfies this statement. This event covers x values. That is, so long as it's bigger than 3/4. All right? But the f of x takes different form over this range. If from 3/4 to 1, it takes the value 2x. And from 1 onward to infinity, it takes the value 0. So that's why you don't see it. All right? Maybe later, after a few more times, I drop this part. Understood that because we don't have this, because the integrand is equal to 0. Because f of x equal to 0 over that range. All right? So you just integrate 3/4 to 1 to x dx. So the answer is 7/16. Oh. Okay. Example 2. So we have this definition of this term called time headway in a traffic flow, which is the elapsed time between the time one car finishes passing a fixed point and the instant that the next car begins to pass that point. So it means that if the car in front of you got 3D effect, probably all becomes same color. Okay, so if the car passes through this point, all right, to recognize time 0, then your car, the next car start passing through this point, then that is the time is called time headway. All right, it's important. I don't know whether you know how to drive or not, right? You know what is the time that you leave. I mean, you make sure that your time headway is within certain value. You know what's that value? What's the time? Anyone knows? No one knows. On the safe side, do you know? Anyone knows? Time. Can it be 0? Can it be 0? Unless you hit the car, 0, right? It just passed and then no time, then you pass the same point. So that means you kiss the backside of the front car, all right? Can it be 0? All right. Can it be 1 second? Yes, can. 1 second is still at some distance. All right. I don't know whether you have done this experiment. Ask you to press a button. So everyone thinks I can hit it immediately. And immediately means some time. I don't know, but at least it takes some time. So the same applies to you press the brake. You lift your leg, your foot, and press the brake. It takes some time. It cannot be 0 second. And not only that, the car needs the time to respond. You think the time you press the brake, the car will stop. No. If you learn physics, you know that the car will continue to go even if you lock the brake. All right? So, when I learned how to drive, I was told that you live 2 seconds. And it's also good. Depends on the second. All right? What does it mean? It means that if we go very slow, I live 2 seconds. It's still okay. That means I can have a shorter distance. All right? But if you go very fast, okay, let's say the distance is, let's say 10 meters. All right? 10 meters, no, maybe 10 meters, okay, 10 meters. So what I mean is that if you go very slow, then it's more than 2 seconds that you pass this 10 meters. All right? But if you drive very fast, 100 kilometers per hour, then the 2 seconds will have a long distance, longer than when you travel at 10 kilometers per hour. So we convert it to seconds. This is what time headway means. All right? So 2 seconds should be okay. So make sure that, okay, this is the point where the front car passed. So when I reach that point, it's after the 2 seconds. Then I keep a safe distance with the front car. How to count 2 seconds? 1, 2. You can count 1, 2. I count 1, 2. 2 seconds. So, you see, sometimes you have to know how people think. So, the rule I was told is that count like that. 1001, 1002. That is 2 seconds. Right? 1, 2. 2 seconds. It's less than 2 seconds. So, 1, 2, that's more than 2 seconds. So they just normal speed, 1001, 1002. So that's 2 seconds. This is good, huh? No statistic, no numbers, nothing. So, okay. Now, so x is the time for headway, and it follows this. Is it ugly, huh? Yeah, very complicated heading, how to do integration for exponential functions. But the exponential function is a very beautiful function. Why beautiful? It got a lot of nice properties. Did you know that? Okay, when you differentiate x squared, what do you get? 2x. All right? But when you differentiate e to the power x, what do you get? E to the power x. Differentiate again, you got e to the power x. Wow, so nice. Right? And also, ex can be expressed as a Taylor series. All right? So it's a very nice form. Anyway, ex is so beautiful that you will like it. Especially when you come to normal distribution. Right? Your calculator will not show you e to the power something, but yes, it is based on the exponential function. All right. Okay, so this is PDF, and only valid for x bigger or equal to 0.5. All right. Why not x bigger or equal to 0? As I said, it does not make sense to have your time headway of 0 seconds. That means you already kissed the car in front of you. So start with certain distance. So I don't know, 0.5 is correct. It's a real practical number, but this is just saying that it cannot be 0. You start with some headway, a distance away from the previous car. So now the next question is this bigger than 0? This function over this range. So that's one thing that you have to know. Is this bigger than 0 for all x? Even negative? Is it? What is e to the power minus 1? 1 over e, right? Use a calculator, you know what is e. I don't know what is e, but I roughly know that it's 2.71 something. All right? So what I'm trying to say is that, okay, so this is bigger or equal to 0, no matter what your x is. All right? So even x bigger or equal to 0.5 is bigger than 0, bigger or equal to 0. And also you have to know whether integrate from 0.5 to infinity, this expression equal to 1. All right. So you can check lah. All right. Okay. So what's the question? Oh, so it's just an exercise to show all this. All right. Usually when you work on integration with exponential functions, this technique is called integration by parts. Have you heard of that? Have you used it before? Yeah, you remember now. Integration by parts. So integration by parts will be used for, quite commonly used for integration with exponential function. At this point, we don't need it. And in fact, I just a little bit sidetracked about the computation. This times this give me this, give me this part. This times this gives you a constant. So it's e to the power minus 0.15 times minus 0.5. Now this is a constant. It does not involve any x. So I bring it out. So this is the part. All right. So what I'm trying to say is that it looks complicated, but if you know how to simplify it, it's not that complicated. So this minus 0.05 times 0.15 times 0.5. You can bring it out because it's e to the power that number is a constant, so you can bring it out. Then you do the integration. So remember, integrate e to the power x dx. All right, the answer is 1 over a e to the power ax. If I have no limit, then I add a constant. If I have a limit, then it is, too many a's. Let's say c and d. So it is equal to c to d. All right. Am I right? Is that the answer? This one, is it correct? Let me put a question mark. All right. So go and check. Sometimes I intentionally or sometimes unintentionally make a mistake. All right. Okay, so I just showed you that this is true. If bigger than 0, the f of x bigger than 0 and is equal to 1. All right. So it's a legitimate probability density function. Hey, you don't want to work on something that is not a PDF. And then after you work so hard and they say, oh, this is a probability of such event. But in fact, that is not a proper PDF. So you waste your work. All right, so I just showed that is correct. All right, but in the test or in the exam, I guess if you are not asked to show that it is a proper PDF or proper probability function, you don't need to check. All right, that's my feeling, but I'm not the one who make the decisions, right? So what I'm trying to say is that you look at it. If the question, all right, did not mention about ask you to show that it is a properly defined, then don't waste time to show that, oh, this is bigger than 0, and do the integration, this is equal to 1. Right. You're taking so many tests or exam already, you know. So what I want, like what the examiners want from your primary school, secondary school, you want to know how, what you know. So here, if I want to test you whether you understand the definition of probability function or probability density function, I will ask you, yes, show that, or find this C, or show that this is a proper PDF. If I ask you to, okay, compute this probability given this one, so you don't have to check, you can assume that this is correct and then start finding the probability. All right. Hey, you are the one who sit for the exam or test. 1 hour for the test, 2 hours for the exam. Don't spend half an hour trying to show that integration from minus infinity to infinity f of x is equal to 1. And you may got 0 marks, because that's not what we want. All right, so you have to understand what you are supposed to answer, or what you are asked. Okay, what's the probability that the head wait time is at most, cannot bigger than 5. So, translate it means probability of x at most 5. So it's like that, right? Am I right? Oh. Is there any difference between this and this? In terms of English, of course, this is correct. At most 5, you can have 5. But in terms of the probability, because x is continuous, so it doesn't matter. But it better brush up English. At most 5 means that it can be 5, right? So you have to write it like that. Although I'm not testing your English, I just want the answer. But it makes a lot of difference when x is a discrete random variable. All right? So the answer for these two probabilities, x less than 5 and x less than or equal to 5, are the same when x is continuous. But when x is discrete, it may not be the same. All right? So we still have to brush up our English. Make sure that you know at most 5 means less or equal to 5. It can be 5. All right? At least 5. What is it? X greater or equal to 5, including equal, at least. All right? Okay, so just do the integration. So this is the answer, 0.49. All right? Cumulative distribution function. So many functions. So far, we just covered two. One, in fact, the two are the same, but one for continuous random variable, one for discrete random variable. Both tells us something about how likely or the probability or probability density of the random variable take of certain values x. All right? So that is probability function or probability density function. Sometimes people don't care, just use probability function to represent both. All right? But here in this chapter at least, I use probability density function to tell you that that function represents the density, the probability density of the random variable. And that is for continuous random variable. Now for cumulative distribution function, it basically is this one. All right. It is the cumulative. Basically, it's the cumulative probability. So what does it mean? For discrete case, let me use this one. All right. So this is x. This is f of x. For x equal to this is the probability. X equal to this value, this is the probability. So now I ask you, let's say 1, 2, 3, 4, 5, 6. Then I ask you, what is the probability x less or equal to 2? We know that in chapter 1. This is probability of x equal to 1 plus x equal to 2. Right? Am I right? So you have add this and this together. All right. So for continuous, all right. So I want to know what is the probability x less than this particular value, let's say a. So what is it? So it means that you are getting this area. So you have to collect all the density for any x value which is less than a. You collect the PDF. So that is basically getting the total probability under the curve up to the point A. This is the definition. All right? And this definition applies to both discrete and continuous random variable. Cumulative, remember cumulative. That means you add what? Add those probability or density up to the required value x. Any value less than it, we'll grab it, put as our part of our cumulative distribution function. So here's the picture. All right. For discrete random variable, so this represents the probability function. So at this point, you see, at this point, the probability function is 0. There's no line here. So at this point, f of x, little f of x is 0. But at this point, the cumulative probability is not 0 because you have to add this probability, this, add all together. So this is the part, the sum of all these four. All right. Now, because even if you collect all this probability, it is equal to 1. So therefore, the CDF is ranged from 0 to 1. From 0 to 1. This f of x, which must be between 0 and 1. Because this represents the cumulative probability. It cannot exceed 1. This referring to how likely you see the random variable takes the value less or equal to x. All right? Okay. Then now how about the mathematics part? The mathematics part. So I want to find this probability of x less or equal to x. All right. So this is called f of x. So I write it in this way. I sum f of t. Now t is an argument. So t can change. All right. So what I want is that so long as the t is less or equal to x, I will include it in this summation. This summation means that you are summing up over summing up a bunch of f, the probability function. Evaluate at the value t. This t can be any numbers so long as it is less than x, less or equal to x, less or equal to x. All right? So this is what it means for discrete random variable. So my point is that sometimes you're confused about the running index and the functional, the arguments. All right. Now this is the argument. I fixed this little x. It can be anything. Here, this t is a running index. That means it's a subscript. It is an index to identify what are the ft. So long as t is less than x, it will be part of this summation. So, for example, let's say this is 10. I want to know what is f10. Then what I have to do is to add, suppose f of x only defined from 1 onward. So I have to add 1, 2, up to f10. All right? So that's what the summation sign means. So the running index represented by t. So this is t equal 1, t equal 2, t equal 3, up to t equal 10. And how to pick up this number? These numbers are all less or equal to this x. So t less or equal to x. All right? So, now one important feature about the CDF for discrete random variable is that it is a step function. What is a step function? Well, you see there are steps here, right? So it's step 1 flat, all right? This is not a step function. This is a slope, right? You climb the slope. This is a step function. And a step function, usually this will be at the same height, same line. All right? You cannot have usually you will not see something like this. What I mean is that with a big gap here. With a big gap here. For CDF. For CDF, it must continue. The range, all right? In other words, for any x value, you can find the capital F of x. If the function like that, then what happened to the x value here? You may not able to find any capital F of x. And I don't know whether you noticed. Is there any difference between these two? Can you see in your notes? One is a solid circle. The other one is just a circle. All right, it's not solid. So, in mathematics, the solid one means that you have the value there. For the circle, that one, it means that there's no value there. All right. So what I mean is that, let me use my magnifying glass just for this part. What it means is that, okay, the function has value here. Continue until it reach certain point. All right. Once it reach that point, it will jump. All right. So that's why this point, this empty circle, you just go there. Once you reach there, before you reach there, you're still at that level. But once you reach there, you jump. So that's why it's empty, because you don't have the value there. The value is up. You already jumped to here. So this point, no value, but then the value changed to this point. So that's what the graph means. All right, so for any two numbers, a and b, a less or equal to b, then f of probability of x between a and b is defined as f of probability of x less or equal to b minus probability of x less than a. Now it's important you have to understand. Okay, first of all, from the definition, f of x is defined as the probability of random variable less or equal to x. All right. So now this part is x between a and b, including a. So that's why it's written as probability of x less or equal to b minus x less than a. All right. If you go back to this graph, So for example, I want to find out what is the probability x between 2 and 4. Then it's equal to probability of x less or equal to 4 minus probability of x less. If I do this, then that means I subtract away the x equal to 2 probability. All right? Which is not what we want. I want to include 2, x equal to 2. Therefore, this cannot be less or equal. This has to be less than 2. Less than 2. This is very important, especially when x is discrete random variable. If it's continuous, we don't bother. But when x is discrete, it's very important you have to know, understand why it says so. All right, so in this case, you have to minus, so it's this one, x less than a, probability of x less than a. But this is not f of a. These two are not the same. F of a is probability of x less or equal to a. All right? So, then what to do? So we define this a with a superscript negative. It means that it's a number. It's a number less than a. Just slightly less than a. Okay? So we minus that. So a with a superscript negative is the largest possible value of x that is strictly less than a. So in other words, if a equal to 2, then what is a minus? 1.9? No. 1.99? No. 1.99? It's just a number which is close to 2. It is 1.9999999, many nines. All right? It's just a number close to 2. Very, very close to 2. But for our contest, discrete random variable, usually the range of x takes the value integer. So probability of x less than equal to 1.99. Are they the same? For our discrete random variable, they're the same. Where you got the probability for any values, one x value between 1.00001 up to 1.99. They're all 0, nothing there, no probability there. So it's the same as probability of x less than or equal to 1. All right, for discrete case. All right, so this is how we do it for integer range for the random variable x. So this is what we usually have for discrete random variable with integers as the range space. So from here, we can get probability of x equal to a. So it's equal to f of x minus f of x minus 1. All right? And remember, this capital F is the cumulative probability. Cumulative probability. Less or equal to a minus probability of x less or equal to a minus 1. So the difference is probability of a. Probability of x equal to a. This only applies to discrete random variables. Remember, discrete random variable. Then how about continuous random variable? Okay, so this is the CDF. This is the PDF, probability density function. This one, all right. So x at this point, then this is the little f of x, f of at this point. While CDF is this, the height here is this probability. So this, again, we use the definition. It's equal to probability of x less or equal to x, and this is equal to this whole thing. All right. Now, let me repeat it again, the difference between t and x. Don't write something like that. What's wrong with this statement, this integration? you have x everywhere. Is this x and this x are the same thing? They are all x, but they are different. One is the integration limit, and this x referring to this, you specify this x value. While this is not, you can call it another name because this is just the integration argument. You can change it to another letter. Here I use t. Okay, to differentiate that these two are not the same thing. Okay, I'm doing the integration over a function, the argument, let's see, I call it t. So I integrate over ft with respect to t. But the integration limit is from minus infinity to x. Why x? Because I want to compute the CDF at x. That means capital F of x. I want to compute this one. So this x appear here. All right? This is just an argument, an integration argument. All right. So how to get back the PDF from the CDF? For discrete, we just talk about f of x, f of a, which is probability of x equal to a, is equal to f of x equal, f of a minus f of a minus 1. All right? But for continuous, it's even easier. You just differentiate the CDF. Right? I don't know whether you remember that. This is how we got. This is how we got the CDF. That means we obtained this CDF from the PDF. So how to get the PDF from CDF? You just differentiate this with respect to x. Then you get f of x. All right. All right. This is properties of calculus. I think, if I remember correctly, okay. I forgot all this. I don't know whether it's called first fundamental theorem of calculus, but this is the properties. All right. So what I want you to know is that how to get from 1, that means the probability function or probability density function, to get to the cumulative distribution function. There are only one formula for that. While for PDF and probability function, they are formula, and this formula, how you deal with it, depends on whether it's discrete or continuous. But the definition of CDF is just one definition. It's probability of x less or equal to that lead to x. All right. So now, if you are given a CDF, how to get back to the probability function? So for discrete case, you check the difference between the two consecutive two consecutive probability function. While if it's continuous, you differentiate it, and you get back the PDF. Of course, provided that the derivative exists. If it does not exist, then no. All right. So because of that, so the probability of x between a and b is equal to f of b minus f of a. Not because of that, but you can show that it's like this. So it's very, very easy. You just substitute b into the CDF and substitute a in the CDF and then take the difference. And this f of x is non-decreasing function. Is it obvious? Oh, non-decreasing function means that if a is less or equal to b, then f of a must be less or equal to f of b. That is what we mean by non-decreasing function. It won't drop, and it's obvious. Why? Because if your b is bigger than a, so besides the probability that you collect up to a, you still collect all the probabilities or density between a and b. So of course, fb must be bigger or equal to f of a, right? So it's non-decreasing function. Look at the picture there. It's an increasing function here. Increasing function. Look at this one. Discrete. Is it a non-decreasing function? Of course, yes. All right? if you take these 2 points, then the f of f, capital F at this point and capital F at this point are the same. So it does not decrease. All right, it's non-decreasing. But if you take this point and this point, these 2 points, then of course f of the capital F at this value and capital F at this value, they are, one is less than the others. All right, so it's non-decreasing function. And f of x must be between 0 and 1. Okay, let's look at an example. So suppose the PDF is given, probability function is given by this. Is this discrete or continuous? This random variable. Discrete, continuous, discrete. All right, takes integer, discrete. So if you know that it's discrete, then what you do is going to do sum, not integration, not integration. All right. So now we are asked for any positive integer x, calculate the CDF at x. All right. So that basically we just add. Wow. So here you need some mathematical skills. So what is ft? Ft will be 0, or at least start from, so basically it's f1, f2, up to f of x. All right? So that's why I sum t from 1 to x. This is what we mean by change this t, start from 1, then 2, then 3, up to x. All right? So in other words, it will be 1 minus p, 1 minus 1p, plus 1 minus p, 2 minus 1p, plus and so on. All right, just change this one until you reach the last term, which is 1 minus p to power x minus 1 times p. How to do this sum? All right. Usually working on this sum is quite hard. All right. But there are some obvious techniques. One is called geometric series. Right? Remember what is geometric series? If you see a number, right? All right? That means that each term, you just multiply the previous one by r, by the same constant. To make it more complicated, this is again also. All right? You just multiply the previous one by r. All right? So ignore this one. This one just take a as a common factor out, so it's okay. All right? Then this one, what is the sum? So suppose I sum, in fact, if you sum to infinity, you know the answer? So nice, 1 over 1 minus r. All right? If you don't know, you forgot, go and do the divisions. 1 divided by 1 minus r. Divide it. How to divide it? So go back to check your algebra, how to divide it. So you will get this sequence. All right? But what happens if I just sum up to, let's say, k of them? Then what is it? 1 minus rk plus 1 over 1 minus r. All right? But you have to remember one important thing. All right? R has to be less or equal, the absolute value of R has to be less or equal to 1. Think of it, if R is 2, let's say, then it's 1 plus 2 square plus 2 cube. You cannot add. Okay, add up to, okay. What I mean is, you cannot add infinite number of them because the series will not, we call it divergent. All right? But for finite, it's okay. So you can still apply the formula. All right. Okay. Besides geometric geometric series. There's another technique which may be special for the probabilities. Remember I mentioned earlier, for discrete random variable, the sum of the probability function is equal to 1. That means sum of the probabilities for all possible value of x should equal to 1. So that one is also used for doing summation. All right, but someone has proved that lah. Then you can use. Okay, continue with this one. So every term has p as a common factor. So I bring it out. P. And then basically this is my R. And some R, all right, some R. And this S from 0 to x minus 1. How come suddenly it is from 0 to x minus 1? Because I just replaced S equal to t minus 1. So this becomes S. And when t equal to 1, S equal to 0. So I have this one. When t equal to x, then of course S equal to x minus 1. All right? So now this one is equal to like that. Okay? And the beauty is that, okay, 1 minus 1 cancel out and left with p. And p cancel with this p. Wow. So it's equal to this. For x equal to 1, 2, 3. All right? Now, but this is not good enough. The CDF must define for all x value. You cannot just tell me that, oh, this CDF equal to this expression where x equal to 1. Well, where x equal to 2 is equal to 1 minus 1, bracket 1 minus p to power 2. I want to know what is x. What is the f of x where x equal to 1.5? Where x equal to 1.5. Can I use this formula? Can I put this as 1.5? No, because the derivation here is based on x being integer. But we just show that if I want to compute for discrete case, this equal to what? F of 1, right? An integer which is the largest integer less than this value x, which in this case is 1.5. So how do I incorporate this one? So I'm going to write it. Yeah. So I write it like that. This is not x, with a funny bracket. It means that, so here I define it. It is the largest integer less than or equal to x. So if you have 1.5, let's say I want to have f 1.5. And 1.5 is bigger than 1, bigger or equal to 1. So I use this expression and I substitute 1.5 here. So a square bracket 1.5, according to my definition, it is the largest integer less or equal to x. So less or equal to 1.5. That integer is 1. So it's equivalent to f1. All right? So that's how you get the expression. Now, how about this one? So we have number of, x is the number of days of sick leave taken by a randomly select employee. Now let me re-emphasize again. X is a random variable. It's not because the number of days is random, but because we select a random unit. All right? So we select an employee randomly, and the maximum allowable sick days per year is 14. So it is 0 up to 14, including 0. You may pick an employee who never take any sick leave in that year. Why no 15? Can you sick for more than 15 days in a year? Yes, you can, but then you only can get 14 days. So the other day, either you got no pay or you have to take your holiday leave, right? So that's why the number is from 0 up to 14, because this company has a policy of only 14 days for sick leave. Yeah, if you're sick, after 14 days leave, then you either go back to work, or you take no pay leave, or you take your holiday leave. Okay, these are the corresponding CDF. So how to get back to the PDF? Or in fact, it's not the PDF, not the probability function. We just want to compute this probability. So this is equal to F5 minus F, capital F, of a number slightly less than 2, which is the same as 1. So I just calculate F5 minus F1. And x equal to 3 will be F3 minus F2. So it's 0.05. Okay, so here is another example. So manufacturers have this quality control programs. So we inspect the incoming materials for defects. So if the computer box we receive in the logs of 5, and we select 2 of them for inspection. So these are all possible inspection. There are 5 items. All right. So we pick 2 only. So suppose bots 1 and 2 are the only defectives in the logs of 5, and 2 bots are chosen randomly. So determine the x, which is the number of defective bots. All right? And find the probability function for x. So first of all, and then find the CDF. Okay, so first of all, we have 5 items, 1, 2, 3, 4, 5. Name it 1, 2, 3, 4, 5. We pick 2 of them, so these are the possible choice. Unfortunately, I use a bracket, but this order does not mean much. It's just saying that item 2 and item 3 are selected. Okay, so they're altogether 10. All right, so x is number of items that are defective out of 2 that you choose. So x takes a value 0, 1, or 2. All right. So when there are no defective, means that you take these 3 out of all the 10 possible choices. So it's 3 over 10. F of 2, that means you select 2 and happens that both are defective. That means you pick up this one. It's 1/10. This one is easier to work with, right? For F1, it's hard to work with because you have to consider what are the possible sample points. You can think of it like this. To choose, so you divide, for the 2 defective one, you choose 2. For the remaining 3, you choose 1. So that gives you, sorry, 0. So the remaining one, you don't choose anything. So this one is equal to 1. This is referring to this one of them. In fact, I identify what is it. Then this one, no defective. No defective means that from the defective one, I choose nothing. For each combination, I have to take 2 out of the 3. So I don't have to list out. I'm able to find out how many ways. All right? From the 2 defective, I select nothing. From the 3 non-defective, I select 2. So altogether, there are 3 ways. So 3 over 10. All right? So it's easier to work with 0 and 2. 1, still okay. 1 means that the 2, you choose 1. All right? And then the 3 non-defective, you also choose 1. So altogether, there's 6. All right? So it's 6 over 10. So to write it down, this is our probability, the probability function. All right? Given value 0, this is the f0. Given value 2, this is the f of x. All right, so all this, and also I take care, if x does not equal to 0, 1, 2, it's equal to 0. All right. Lastly, to find the CDF, so I just sum up the probability. So f of 1, sum up probability x equals 0 and x equal to 1 is 0.9. And x equal to 2, the probability, the cumulative probability equal to 1. So basically just do the addition. And there are only 3 probability functional value. So just add those. So this is a CDF. All right? You cannot write in a table form. I express it in terms of the range. For any x up to 0, this is f of x. Basically, this is a step function. Up to 0, this is 0. And then between 0 and 1, it jumps. This is 0.3. Then from 1 to 2, it jumped to 0.9. All right? And then from 2 onward, it becomes 1. So this is the PDF. The CDF. This is the graph. I just express it in terms of this. I divide the x into 4 parts. 0 to minus infinity to 0, 0 to 1, 1 to 2, and then 2 onwards. So each one has their own value for this CDF. All right? Okay, I think I stop here. All right. So we'll continue next week.